My name is Paul Newman. I am the Chief Scientist for Atmospheres at the NASA Goddard Space Flight Center. What I'm going to show you is a model simulation of what would have happened if the Montreal Protocol had never been enacted and chlorofluorocarbons had kept increasing. So the basic story is if Sherry Rowland and Mario Molina, as David has already talked about, if they had not discovered the chlorofluorocarbon ozone problem in 1974, what would have happened? So in this model, it's a full chemistry climate model, so it has all the chemistry of the stratosphere. That chemistry changes ozone levels. Ozone controls the radiation of the stratosphere, so the heating and cooling. That changes wind patterns, which then move ozone around. So it is a fully coupled model. It has climate gases in it, CO2, methane, nitrous oxide, and other gases. So it has a complete chemistry in it. So what we did is in this model, we simply allowed chlorofluorocarbons to increase, the emissions to increase 3% each year starting in 1974. That's the year that the Rowland and Molina Nature paper was published. So by 2065, the chlorofluorocarbon levels have increased substantially. In fact, the amount of chlorine in the stratosphere is about 40 times its natural level. I'll get into those levels. They're actually quite tiny amounts. And then, as I've already described, we use this state-of-the-art chemistry climate model. Now, this is a very sophisticated model now. Compared to what they were using in the 1970s, this is many, many, many times more powerful. It really does produce its own atmosphere, Earth's atmosphere. So it's a very sophisticated model. Now let me start off by showing you a couple of pictures. What I'm going to do is I'm going to show you some of the model output. And we measured the total amount of ozone between the surface and space, or we model that. We can also measure it from satellites. And this total ozone is measured in Dobson units. And now, a Dobson unit is a measure of the thickness of the ozone above your head. And so the two pictures on the right are simulations of what in 1974. On the top, what I'm going to call the world avoided, and on the bottom, what I'm going to call the expected world. So if you could bring all this ozone down to the surface, it would form a layer about 3 millimeters thick. That's about 1/8 of an inch. So the ozone in our atmosphere is very tiny amount, yet it screens UV radiation. This is the power of ozone. Now, these are false color images, and low ozone is in blue-purple colors, and high ozone is in red-orange colors. So the two pictures you see on the right there show the global amount of ozone. Now, I'm going to start off by showing you a little movie. So you can see ozone. Here's the color scale. This bottom left image shows the global amount of ozone. So you average over the entire globe and you get the global amount. The top left picture is a picture of the amount of chlorine in the atmosphere. Now, there are two representations on here. The blackish line that you see represents the amount of chlorine in the stratosphere in this world avoided, so this top image. So as I run this movie, you'll see there's a little black dot that'll move up here, and ozone will change over on this right picture. The little red dot shows the amount of chlorine in the expected world. That's this image in the bottom right here. And you'll see the global amounts of ozone change. Now let me see if this movie plays right. Okay, so now you can see the two simulations evolving as a function of time, and you can see the year changing in the middle here. And so the amounts of chlorine were about the same in the 1970s and 1980s. So I'm going to try to stop it here in about the year 2000, see if I can do this right. Okay, so in the year 2000, you can see in the world avoided, in the expected world, the amounts of chlorine are about the same, and the global ozone is about the same. In the bottom of the picture, you can see a little ozone hole down here. So both in our expected world simulation and our world avoided simulation, we get an ozone hole. Let me keep going forward. Now you can see the amount of chlorine in this top left picture is increasing. Because of the Montreal Protocol, the expected amount of chlorine was actually declining. So you get out here to 2012. This is about the same. It's about our date here in the simulation. Now, if you look at the two pictures, you can see up here in the expected world, chlorine has gone up. That's the world avoided in black here. So chlorine now has increased to about 10 parts per billion. Now, what that means is that if you add chlorine and bromine together, there are about 10 chlorine molecules in every billion molecules of air. So this is a very tiny amount of chlorine. Now, the global ozone has gone down. You can see that because of the Montreal Protocol in our expected world, ozone starts increasing. It starts recovering. It stopped declining, and it's going up just a tiny amount by 2012. You can see in our world avoided, though, ozone continues to go down. So it starts off here at about 300 Dobson units or so, and now it's declined 30, 40 Dobson units. And as you continue to roll forward, we'll go out about another 20 years here. And I'll try to stop it here in about 2024, 2025. Oops, not very good at this. There we go. Okay, so now you go out to the year 2028. You can see it in the middle. You can see it in the world avoided up here. Now, typically in the springtime in the northern polar region, you tend to get a mountain of ozone. And you can see this in this expected world. Now, up here in the world avoided, you can actually see that an ozone hole was forming in the high Arctic. And you can see a very prominent ozone hole down here in the Antarctic region. You can also see, if you look in the tropics, you can see ozone levels are lower in the tropics than they are in our expected world. And as we continue to roll forward, you'll see ozone continue to decline as you go to these blue and purple colors. The ozone holes now, as you go through each year, become more and more prominent in both the Arctic and down here in the Antarctic. And as you continue to roll out, you can see ozone further declining. You can see the global levels here plunging as chlorine goes up. And finally, you get to the very end here, and you can see that global ozone has declined by a substantial amount. So the chlorine amounts has gone up to something over about 40 parts per billion. That is 40 to 50 molecules of chlorine per billion molecules of air. The ozone level has dropped from somewhere up here around 300 Dobson units down to about 100 Dobson units. So the basic point is, with a fully coupled climate model, we get massive losses of ozone. Now let me take a look a little more detail. This again shows a plot of total ozone as a function of year, and these are some simulations up here. Here is a green line shows a world in which no chlorine was added to the atmosphere. The blue line shows our expected future, or the past, the simulation of the past. The red line shows our expected future. So ozone declining, the Montreal Protocol is signed, and ozone then increases. Well, what about the world avoided? Well, in the world avoided, you can see this, by the way, this represents April of 1980 and April of 2020, looking down on the Arctic. So you can see this ozone hole. Typically, we have a mountain of ozone up in the polar region. Here, you actually have formed an ozone hole. And then by 2060, you can see that ozone is gone across the planet. There's a very prominent ozone hole up here in the Arctic. You can see the difference between the black line and the red line. A massive amount of ozone has disappeared. Typically in April, you're getting something above around 500 Dobson units in the Arctic. This is an average over the polar region, by the way. I forgot to mention that. And it's declined to something like 100 Dobson units. So about 75, 80% of the ozone destroyed over the Arctic in the month of April. Now, what about the UV index? Let's turn to ozone. As I mentioned, screens ultraviolet radiation. Let's take a look at the UV index. This is a midsummer UV index that I've calculated. It's a function of latitude, so I go from 90 degrees south, or the South Pole, to the equator in the tropics, all the way to the North Pole, and then here is the year. So this is in early July, late June, the UV index in the northern hemisphere. In the southern hemisphere, it would be late December, early January. Now, I've drawn a couple of lines across here. 40 degrees north is about the latitude of Washington, D.C., Northern California. You can see in midsummer, you typically have a UV index value of about 10. Now, that UV index would give a person like me a sunburn, perceptible sunburn in 10 to 15 minutes. That UV index, as you go to further years where there's less and less ozone, by the end here, that UV index is about 30 in the Washington, D.C. area. Now, that would reduce my burn time to less than 5 minutes. So a 5-minute walk, something like a quarter-mile walk, walking around a racetrack once, I would get a perceptible sunburn. You can see that in the year 2012, I marked it with this little vertical line. You can see that the UV index would have increased from a value of about 10 up to something less than about 12. So you're getting something like a 15 to 20% increase in UV in this world avoided. And you can see in the tropics, of course, the UV index is getting higher and higher and higher. So that's the UV index. That's the sunburning index that we typically publish during the summer, all summer months and days when you have nice clear skies. What about crops? Crops are also damaged by UV radiation. So in the top picture, what I do is I've calculated the amount of UV radiation that can damage crops. That UV radiation has increased. This is in percentage increased by something like, this is a 10. So over places like India and China, about somewhere between around 10 to 15% with respect to the 1974 to 1980 average. So it's a fairly large impact on crops. By 2047, you can see that the changes in this damaging radiation have increased. Something like 70% increases over India and maybe 80% to 90% over China. So the impacts of the UV radiation on crops is quite substantial. Even by the year 2011, you're having significant impacts on crops, which will then have impacts on food prices and our ability to actually feed large populations. In addition to the ozone damage and the UV increase, CFCs, chlorofluorocarbons, are actually powerful greenhouse gases. This is a simulation done by my colleague Rolando Garcia at NCAR. It is very similar to our simulation, but they actually looked at surface temperature changes. Now, what they find is on the top picture is a control case. This simply is how the Earth's surface will warm with increases of CO2, nitrous oxide, and methane that we see. CFCs are controlled in this top simulation. And so you can see there is warming, a lot of warming up here in the Arctic. The bottom picture shows the same simulation, but now chlorofluorocarbons have been increased substantially, and you can see the difference. You can see that the orange color, which indicates something like a 4-degree change, is now spread, so it's very small up here in the Arctic in this control run. In this world avoided run, you can see the temperature change in the Arctic is quite substantial. Now you can see large areas where temperature changes are 8 degrees. Now these changes are in Kelvin. If you want to get to Fahrenheit, you can approximately double those numbers. So in summary, this unabated increase of CFCs would have depleted 2/3 of the ozone layer. Now the rates that I used, a 3% increase per year, that's actually a relatively small increase compared to what was happening in the early 1970s before Molina and Rowland discovered the CFC ozone connection. Rates back then were on the order of 7 to 10% increases of CFCs per year. The UV radiation that would result from a depletion of the ozone layer with this very large 2/3 destruction, it would have tripled UV indexes. This would have had also, this increase of UV at the surface would have had really severe impacts on plants, crops in particular. And the direct radiative effects of these high levels of CFCs would have caused an additional 2 to 4 degrees Fahrenheit global warming of the Earth's surface. So with that, thank you for your time, and I think I can pass back to David.